Have you ever stopped to think about how our power grid actually works? I mean, it's this massive, continent-spanning machine, and somehow, it all stays perfectly balanced. And now, with clean energy popping up everywhere, how does it all hang together? Well, today we're going to dive into the incredible science of how we're starting to predict and even control the future of our electricity grid.
You see, our energy world is going through this huge transformation. We're shifting away from just a few big, predictable power plants to a grid that's fed by countless renewable sources, like these massive solar farms. And that, right there, creates a brand new challenge.
And when I say massive, I really mean it. Just look at this solar plant in Australia. It can pump out 220 megawatts of power. That is enough to power an entire small city from just one single field of panels. The scale we're dealing with here is just absolutely immense.
Okay, so at the heart of every single one of these solar farms, there's this super critical piece of hardware, the power inverter. The best way to think of it is as an essential gateway. It takes the DC power that solar panels make, and it converts it into AC power that, our grid and our homes actually use.
But here's the catch. To handle all those megawatts, you need hundreds, sometimes thousands, of these inverters all working together, in parallel. The problem is, even tiny little differences between them can cause them to start fighting each other. They create these invisible circulating currents that just waste energy, mess up the power quality, and can even damage everything. It's a huge problem that makes our grid less stable and ultimately more expensive for everyone. So how in the world do you get them all to play nice?
Well, for years, we've used these pretty traditional controllers to manage the grid. But as you're about to see, these old-school methods just can't hack it anymore. They're not built for the new problems we're facing on this fast, modern, renewable-powered grid.
You see, the classic controllers, we're talking about things like PI or droop control. They are fundamentally reactive. It's kind of like a basic thermostat in your house, right? The room gets too cold, and then the heat finally kicks on. They have to wait for a problem to happen, like a voltage drop or a frequency shift, and only then do they try to fix it. On a high-speed grid, that's almost always too little, too late. And when you put them side by side like this, the mismatch is it's stark. On one hand, you've got the old controllers, reactive, slow, and really sensitive to any changes. But what our modern grid needs is a system that's proactive, that gives us instantaneous stability, and that's robust enough to adapt to the constant ups and downs of sun and wind. There's this huge gap between the tools we have and the tools we need.
And this chart just says it all. This shows how long it takes for the system to get back to normal after a big disturbance. The old droop control method, it takes over 645 milliseconds. This new method we're going to talk about, just 20 milliseconds. That is over 30 times faster. It's the difference between catching a falling vase and having to sweep up all the broken pieces from the floor.
So what is this smarter way? It's an approach called Model Predictive Control, or MPC for short, and honestly, it's a total game changer.
Probably the best way to explain MPC is to think of a chess grandmaster. See, a normal player just reacts to their opponent's last move, but a grandmaster? They're thinking dozens of moves into the future, predicting all the possible outcomes on the board, just to pick the one single best move to make right now. Well, MPC does the exact same thing, but it's playing chess with our power grid.
So how does it work? It runs in this crazy fast, constant loop. First, it uses a digital model of the power system to predict what's about to happen in the next fraction of a second. Then it goes into optimize mode, running through thousands of possible actions to find the absolute best one. After that, it tells the inverter to act on that one perfect command. And this whole cycle, predict, optimize, act, it repeats thousands of times every single second.
Okay, so this ability to see into the future gives MPCs some pretty incredible real-world superpowers. Let's take a look at how this actually builds a more stable, efficient, and frankly tougher grid.
Its first superpower is basically taming chaos. Remember all those inverters that were fighting with each other? Well, MPC gets them all working together in perfect harmony, and that dramatically improves the quality of the power that's being sent out to the grid.
And hey, the data really doesn't lie. Look at this comparison. With the traditional controller, you're getting a power ripple of 7.7%. With MPC, that gets cut almost in half, down to 4.3%. Even better, check out the harmonic distortion. That's basically just electrical noise. It plummets from over 2% down to just 0.82%. What that means is much cleaner, much more efficient power for all of us.
All right, superpower number 2 is its lightning-fast reflexes. The grid isn't always a calm, stable place. Sometimes, because of a fault somewhere down the line, the voltage can just suddenly dip, and that can cause whole power plants to trip offline, potentially leading to a blackout.
But MPC doesn't panic. Because it's always predicting, it sees that voltage dip coming and instantly tells the inverter to inject reactive power. Think of it like an electrical stabilizer, to prop the grid back up. This is called low-voltage ride-through, and it is absolutely essential for keeping the lights on when things go wrong.
Now, this final superpower might just be the most impressive of them all: unbreakable resilience. I mean, what happens if a critical piece of hardware inside the inverter physically breaks down? Okay, so here's how it works. In normal operation, this advanced inverter is designed to produce 13 different, distinct voltage levels. The more levels you have, the smoother and more perfect the AC wave you can create. It's all about quality.
But then, disaster strikes. A critical power switch inside the inverter just fails. It's broken. Now, with an old system, this would be a catastrophe. The entire inverter would just shut down, and that whole chunk of the solar farm would go dark.
But watch what happens with MPC. The controller instantly detects the failure. It understands that its internal map of the world has changed, so it reconfigures the other working switches on the fly and just keeps on going, now producing 9 voltage levels instead of 13. Yeah, it's not perfect anymore, but it's still running. The grid stays on. This is literally self-healing, intelligent hardware in action. It's incredible.
So, what does this all really mean? I mean, these superpowers aren't just cool engineering tricks. They are the actual building blocks for the future of our entire energy system. When you pull it all together, what MPC delivers is a grid that's way more efficient, with less energy wasted. It's more stable, able to ride through faults that would have caused blackouts just a few years ago. It's incredibly resilient, adapting to physical hardware failures in real time. And it even opens the door to smarter economics, allowing systems to decide whether it's better to store energy in a battery or sell it to the grid based on live electricity prices.
And that brings us to the final thought. You know, the biggest hurdle for renewable energy has always been its unpredictability. But when you have controllers that can accurately predict and react to the future thousands of times a second, well, that challenge starts to fade away. It really makes you wonder, if our grid can truly predict the future, what's really stopping us from building a 100% renewable world?